because Zhaoping unfortunately had a little bit of throat ache, and so her voice is low, and so she will try to economize on her voice because it may get worse. And then, so the lecture will be mostly based on a video, and then on a Q&A session. So it's important that you keep very attention. I mean, you watch the video carefully, so as to ask proper questions. Okay. So please, Zhaoping.
Okay, good morning. Thank you very much. So I'm a little bit embarrassed. However, I did make this custom-made video just for this lecture. Okay, so let's start.
This hypothesis has received a strong support by having its prediction of an unknown but strong saliency effect by an ocular singleton confirmed experimentally. It is also easy and intuitive to see that isofeature suppression in V1 can explain the strong saliency effect by a unique feature singleton in a homogeneously featured background. In this example, the unique feature is in orientation. The saliency effect is so strong that this feature singleton is said to pop out to attract attention. And this is a pop out by unique color, or by unique motion or motion direction, or by a unique eye of origin of visual inputs. Focusing on the orientation feature and iso-orientation suppression, we can also intuitively understand why this vertical bar is more salient than this vertical bar. This is because these surrounding bars have orientation quite close to vertical, so therefore this vertical bar does not fully escape the iso-orientation suppression coming from the surrounding bars. However, more subtle and complex saliency effects in these examples are not so easily understandable just by iso-orientation suppression. Often one needs to look at how V1 neurons respond to such inputs. Furthermore, what if we have an input like this one with a uniform array of bars? Now, if the iso-orientation suppression is too strong, then the mutual suppression between these bars could lead to asymmetry breaking, to give such variations of non-uniform outcomes, and such outcomes will be hallucinations. Therefore, we could test this V1 saliency hypothesis further by asking whether V1 mechanisms and its neural responses could also explain a whole body of behavioral data, some of them quite non-trivial, and they have been known for decades. Now, however, it's very difficult to do the experiment to observe responses from millions of V1 neurons to all kinds of non-trivial visual inputs such as these ones. Instead, we can do a substitute by building a V1 model to get simulated V1 responses to answer these questions. So we can ask, can a single neural circuit model explain both the trivial and non-trivial saliency behavior? Is this model really a model of V1, using only plausible V1 mechanisms? Is this model well behaved, such that it will not have hallucinations? Therefore, let's show a V1 model made of V1-like elements. It should resemble real V1 in its responses to physiologically tested inputs, which are less complex. This is a way to calibrate our V1 model to the real V1. We'll use this model to observe simulated V1 responses to trivial and non-trivial visual inputs, and see whether these responses are consistent with saliency behavior effects. And this model can also help us to understand how the V1 circuit computes saliency. So the V1 neurons are modeled as orientation tuned, and the minority of V1 neurons that are not orientation tuned are omitted for simplicity. And although different V1 neurons are tuned to different scales, let's focus the model on just one scale. So all the model residual fields have the same size for simplicity as a starting point. And also the model ignores color, motion, and other features for simplicity. This is because saliency behavior, such as these ones created by spatial arrangements of oriented bars, these are among the most complex and non-trivial. So this model, it has a visual input, and these are the sampling locations of visual inputs, discrete sampling location 1, 2, 3, 4, etc. Here is one sampling location, and we call it a hypercolumn. And here is a zoomed in view of this hypercolumn, and it has 12 edge or bar detectors, and so one of them is colored red for visualization, and one bar detector for one preferred orientation of a V1 neuron. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 discrete orientations in one hypercolumn. So for example, if we have a visual image like this, it has 5 bars in the image, and these are sampled by these 5 sampling locations, and in particularly sampled by these 5 bar detectors. We color them red just to visualize them. Here are some facts about neurons and their interactions in real V1. Some neurons only excite other neurons, and the other neurons only inhibit other neurons. Outputs from V1 to other brain areas, such as V2 or superior colliculus, are only from the excitatory neurons. These neurons are also called pyramidal cells or principal neurons. The inhibitory neurons are also called interneurons, since they do not project outside V1. When two V1 neurons interact by intracortical interactions, the two corresponding residual fields may or may not overlap with each other, but they are not far from each other, since the axons from a neuron to project to other neurons, they only project within a finite distance, typically within a few millimeters on the V1 cortical surface. And the principal neurons tend to project longer distances than the interneurons do. Two nearby principal neurons can have monosynaptic excitatory interactions. Like in this diagram, we have two pyramidal cells. They excite each other, so they are excitatory interactions. These are two inhibitory interneurons. They are connected one with each to the pyramidal cells, and visual inputs coming to these two pyramidal cells, and they can send response further downstream. And so these two neurons are mutually exciting each other. Two neurons can also have disynaptic inhibitions, like in this diagram. Here, these two pyramidal cells, they are excitatory neurons, so they can only excite other neurons. However, they can mutually inhibit each other indirectly via these inhibitory interneurons. For instance, this one excite that cell, which then inhibit this cell. Similarly, this excite this one and inhibit this one. So these two are mutually inhibiting each other. Two V1 neurons, when their residual fields are not too close to each other, are more likely linked by intracortical interactions when they prefer similar rather than orthogonal orientations. In addition, when their residual fields are co-aligned so that visual inputs exciting them could be part of a smooth contour, then these two neurons could excite each other, especially when they are having weak visual inputs. Here is our V1 model schematically. Here are 3 example cell pairs. Each pair is a mutually connected principal cell and its partner interneuron. These two pairs excite each other monosynaptically, and these two pairs inhibit each other disynaptically. Here is an example input image to this model. For example, it could be that this principal neuron prefers a bar of vertical orientation within its residue field, and this bar for the second principal neuron, and this bar for this third principal neuron. There are, of course, many other principal neurons and their respective partner interneurons for other bars at different spatial locations and different orientations. With this input image, the V1 model's responses after these intracortical interactions are visualized above. The thickness of each bar visualizes the strength of the response from a V1 model neuron to their input bar. For example, this principal cell responding to this input bar, so the thickness of that bar is the response level of this neuron, and the response of this neuron forms part of the V1 model's output. This horizontal bar evokes the highest response, since the neuron responding to it escapes the iso-orientation suppression from neurons preferring and responding to the vertical bars. Here is the saliency map from these V1 neural responses. The saliency value at each location is visualized by the size of the disk depicted for each location, evoking responses. So it corresponds to the corresponding neuron's response level to that location, and always the disk is the maximum response among all neurons responding to that location. For example, at this location of the input cross, there are at least two neurons responding, one to the vertical bar and one to the horizontal bar. This saliency value is the maximum of these two responses, not the sum of these two responses. The response to this bar depends not only on this bar's direct input strength, but also on the contextual inputs. Since the corresponding neuron interacts with the neighboring neurons responding to the context, therefore it depends on the neural interactions this neuron has with the neighboring neurons. This is a schematic of this neural interaction pattern. This rectangle depicts the whole visual field. Here are three examples of interactions from three example neurons at the center of each pattern with their respective neighboring neurons. They are identical, these three patterns are identical to each other, except for a shift of their center and a rotation of each pattern to align with the preferred orientation and residue field location of the corresponding central neuron. Each pattern has a limited range. Therefore, each neuron interacts only with neighboring neurons within this range. Zooming in, this is the interaction between the central neuron at this location and other neurons. Each neuron is visualized by a bar with its preferred orientation at its residue field location. For example, this horizontal bar depicts the central neuron at this location, and this central neuron prefers horizontal orientation. Three bars at this location mean that there are three different neurons here interacting with the central neuron. One of these neurons prefers the horizontal orientation depicted by this horizontal bar. The second neuron prefers the orientation depicted by this bar, slightly rotated clockwise from horizontal. And the third neuron prefers the orientation depicted by this third bar, slightly rotated counterclockwise from horizontal. When a bar is solid, the interaction between the neurons is monosynaptic excitation. Therefore, these 5 neurons, represented by these 5 solid bars, receive monosynaptic excitation from this central neuron. When a bar is dashed, the interaction is disynaptic inhibition. Therefore, these 3 neurons at this location receive such inhibition from the central neuron. As a whole, this central neuron preferring a horizontal bar here monosynaptically excites these principal neurons whose preferred visual inputs are more aligned with a horizontal bar here. So that, for example, between this central bar and this bar, there could be a smooth contour linking them together. And meanwhile, this central bar disynaptically inhibits these principal neurons whose preferred visual inputs are not aligned with the central bar here. And all these surrounding bars have their orientation similar to the horizontal orientation for this central neuron. And such a qualitative pattern of interactions, sometimes called a bow tie interaction pattern, seems to be what's present in V1, as we will show later. If we restrict to just the postsynaptic neurons tuned to horizontal orientation, like this presynaptic neuron, then these are the postsynaptic neurons, colored red for visualization. Here is another schematic to illustrate how it works with this sub-network of V1 containing only the horizontally tuned neurons. And this is a layer of parameter cells, and this is a layer of inhibitory interneurons, one-to-one matched with the principal neurons. Only this one-to-one match is indicated to avoid cluttering in this schematic. This is a presynaptic parameter cell. It projects to these neighboring parameter cells, exerting monosynaptic excitations on them. It also projects to these interneurons, which in turn inhibit their partner principal neurons, which are therefore under the disynaptic inhibitions. From this neuron, these other neurons with a minus sign marked in them and its own partner neuron receive directly a monosynaptic excitation from it. So if we have 5 input bars in this visual image, they directly excite these 5 principal neurons. The central bar monosynaptically excites the bar to its left and its right, and disynaptically inhibits the other 2 bars below. Responses from the parameter cells are visualized here. They are the outputs from this V1 model. Because of the interactions in this V1 model, although these 5 bars have the same input strength, they evoke different response levels. A photograph could be sampled by the V1 model neurons through their classical residue fields to give this as inputs to the V1 model, to give such a model response pattern. We have schematically shown the V1 model qualitatively. Next, we need to specify more details, such as the properties of individual principal cells and interneurons, how they respond to inputs by changing their firing rates, etc. And very critically, the quantitative details of the neural connection patterns between neurons, and which ones are excitatory, which ones are inhibitory, and the synaptic strength, and these are very critical for the model behavior, and of course other details. And all these details need to be calibrated to make the model resemble the real V1 and be well behaved for saliency behavior. First, let's start with some notations. Let I denote a spatial sampling location, 1 for each hypercolumn. So therefore, I equals to 1, 2, 3, 4, etc. to cover all the spatial location, as many as needed. And then for each sampling location I, there are 12 edge detectors. Yeah. So each is denoted as theta for the preferred orientation of each of these detectors. So starting from vertical orientation, rotating clockwise from vertical, and that's theta equal to 0, 15 degree, 30 degree, 45 degree, etc., covering the whole spectrum of orientation evenly. And for example, this red bar visualizes a theta value of 150 degrees rotating from vertical clockwise. For each I and theta, there's a pair of neurons, one principal neuron and one interneuron. The direct input to this principal neuron is denoted as I with subscript I and theta, and xi theta denotes the state of the principal neuron. It can be understood as modeling the membrane potential of this neuron, and with this membrane potential, the firing rate from this neuron is a sigmoid function of the state x. It's non-negative with a threshold and saturation. And similarly, we can denote this yi theta for the state of the interneuron, which gives another firing rate with that state, which is another sigmoid-like function. And the critical difference between these two is that this is not a scaled version of that one. And also, the slope gets steeper as the state gets higher, and the saturation is so far away that one can more or less ignore it. Now you can see the book for details on why these are designed this way. Therefore, if we focus just on one pair of neurons, I and theta, they follow such neurodynamics. For the principal neuron, the derivative in time of its state x is driven by firstly the external input, I, and then the inhibition from the interneuron, and for the interneuron y, by the excitation from the principal neuron. Additionally, the neuron has a self-decay turn back to its resting state when not driven by inputs. And similarly for the interneuron, the principal neuron has in addition a self-excitation. Now let's include the neural inputs from neighboring neural pair at a different location J and preferring orientation theta prime. And this gives the monosynaptic excitation term, which increases with the synaptic weight between I theta and J theta prime. And this synaptic weight across pairs of neurons is the connection matrix, capital J. And of course, the monosynaptic excitation grows with the activities of the presynaptic cell, J theta prime. And now let's look at the disynaptic inhibition between these two pairs. This inhibition comes from a drive from the principal cell X to the inhibitory interneuron Y with synaptic weight matrix W, which is analogous to the matrix J above. And of course, this drive grows with also the presynaptic activity. For this presynaptic neuron, the monosynaptic excitations come from these neurons more aligned with itself, and disynaptic inhibitions come from these neurons, these neighbors not aligned with itself. And both types come from neighboring neurons preferring orientations similar to its own preferred orientation. So when all the contextual bars J theta prime have the same orientation as the central bar I theta, then the net effect will be an iso-orientation suppression when the total disynaptic inhibition overwhelms the total monosynaptic excitation. So now these terms describe details within a single EI pair or a pair of neurons, one excitatory, one inhibitory. These are for interactions between EI pairs in different hypercolumns or locations using such a bow tie pattern of synaptic connections. In addition, we also have suppression within a single hypercolumn or location I, between EI pairs tuned to different orientations. For each orientation theta and another orientation theta plus delta theta, there is a disynaptic suppression by this synaptic strength psi, depending on the orientation difference delta theta. This suppression within the hypercolumn is also in real V1. In addition, we have this activity normalization term to exert a general suppression to a principal neuron by local neural activities regardless of their preferred orientations. Also, this turn to the interneuron could be used for exerting top-down control from higher brain areas. Typically, it should not be used to demonstrate the bottom-up saliency. Each neuron also receives independent noise. This serves to show that the model is robust for saliency behavior. A model detail is the relationship between an input bar at a particular location I with orientation theta and the actual input values I to all the EI pairs in a V1 model at this location. So we denote the input bar in the visual image as I hat with a hat on top of it, but the input to the EI pairs is just I, as we have been doing so far, yeah? And so if the input bar has an orientation theta, then the EI pair preferring the theta is activated, yeah? And so are the nearby EI pairs preferring orientation near this theta, and they are also somewhat activated. And simply because V1 neurons have a finite orientation tuning width, although these EI pairs far away from their orientation are not activated. And this is characterized by this relationship with model parameter function phi. We have many model parameters. The most essential ones are these neural connections, and they are for interactions between nearby neurons tuned to similar orientations. We need to design all the model parameters to satisfy these conditions. Firstly, the model's responses to prototypical, physiologically already tested inputs are like responses from real V1. Secondly, the model is well behaved so that it does not show hallucinations. See the book for how the model parameters are designed. After this design, the model does resemble the real V1. Let's first show this using input bars with medium to high input contrasts in these 4 prototypical inputs, A, B, C, and D. Each pattern is a small portion of a much larger input image extending beyond the boundaries of each pattern plotted. The first row shows the model inputs. All these bars have the same thickness, visualizing that these input bars have the same input contrast. The second row shows the model response levels. The thicknesses of the bars visualize relative response levels. In particular, let's look at the vertical bar at the center of each input image and their evoked responses. When there's no surrounding bars, it evokes a high response. With iso-orientation neighbors, it evokes the weakest response, suppressed by iso-orientation suppression. With randomly oriented neighbors, it evokes a somewhat less suppressed response. With orthogonal neighbors, its response is least suppressed, and this response is slightly less than when there's no surrounding bars. It pops out of the surrounding bars, since the responses to the surrounding bars are much weaker. The suppression therefore depends on the details of the contextual inputs. And here we see no hallucinations of inhomogeneous response to homogeneous input. All these model responses in A, B, C, D are qualitatively like those observed physiologically in real V1. Now let's examine what happens with weaker inputs. In E, F, G, H are examples in which the central bar has a weaker input contrast, and we examine how their responses depend on the context. With no surrounding bars, its response is weak. With one strong neighbor completely aligned to it so that they could link up into a straight line, its response is enhanced. We call this contextual bar a collinear neighbor, and this response enhancement a collinear facilitation or collinear enhancement. Slightly more facilitation with two collinear neighbors. Here is collinear facilitation with concurrent surround suppression. The net effect is still facilitation. These are examples of collinear enhancement to responses to weak inputs, as observed physiologically in real V1. For these 8 prototypical examples, A, B, C, D, E, F, G, H, the V1 model has the same set of model parameters. With stronger inputs, it explains the surround suppression. With weaker inputs, it explains collinear facilitation. In either case, surround inferences depend on the context. They also demonstrate the contrast dependence of contextual inferences, as seen in real V1. Meanwhile, hallucinations are prevented. It turns out that mathematically, to prevent hallucinations while having the desired contextual inferences requires that each EI pair of neurons is not simplified to a single phenomenological model unit, which can excite some neurons and inhibit other neurons. We leave these mathematical details in the book. Now that this V1 model is calibrated, it can be used to obtain simulated V1 responses to visual input patterns not yet tried in physiological experiments, and we can see whether the V1 responses are consistent with saliency behavior. For this hypothesis, we have built and calibrated a V1 model to resemble the real V1 on physiologically tested prototypical visual inputs. Now we can use this model to examine simulated V1 responses on other visual inputs to see whether the responses are consistent with human saliency behavior according to this hypothesis. Before we start, let's quickly see what we can expect from our model, which has such a bow tie pattern of neural connections. When there is an orientation singleton in a homogeneous background, this singleton escapes the iso-orientation suppression experienced by typical background bars, so it's the most salient in such an image. The iso-orientation suppression is achieved by having the disynaptic inhibition overwhelm the collinear facilitation. When we have a bar in a smooth contour, this bar could evoke a higher response than the typical background bar because the model has the collinear facilitation inspired by physiological data. When we have a texture border, this border bar is under collinear facilitation from above and below, and iso-orientation suppression from the right side. However, for a non-border bar, the suppression is additionally from the left side, making the response lower. This is analogous to the situation in any typical texture bar away from the texture border. As a first example, these two neighboring textures indeed evoke such a response pattern, with strongest responses to the texture border bars. Meanwhile, these border bars to the left do not evoke responses as strongly because each is suppressed both from above and from below, but collinear facilitated mainly or only from the left. These bars are more suppressed than usual since they have stronger neighbors from their left. These bars are slightly less suppressed since they have weaker neighbors to their left. These side effects of contextual inferences can be manifested more apparently in later examples. Except when explicitly pointed out, all our plotted images are just small parts of larger images, extending beyond the outer boundaries. Otherwise, the texture bars near the outer boundaries will also evoke higher responses, just because there are fewer neighbors to give suppressions. Since the neural circuit is dynamic, the model responses actually change with time, so the plotted responses are actually temporal averages of the neural responses. Here is a plot of the responses across columns of textures with these column numbers 1, 2, 3, 4 as in the horizontal axis here, assuming that the model input appears at time 0. So these are response levels as function of columns at different time instances for each different curves. As expected, When the input texture bars are left-right symmetric relative to the texture border, the responses are also symmetric, with highest responses still on the texture border bars. This makes the texture border salient, making texture segmentation easy. To better evaluate our model for saliency behavior, let's give a reasonable quantification of saliency values from the model responses. Recall from the V1 saliency hypothesis that the highest V1 response from each location is the bit for visual selection exogenously. So therefore, the model's bit at location I is this value Bi. The average bit across location is denoted as B bar. The standard deviation of the bits across locations is sigma B, and we quantify the saliency at each location I by the z-score, defined like this. Accordingly, at this border location, the z-score is 4, and it's quite high, so this border pops out to attract attention. Here is another example. This is the input to the model and the model response pattern. And here is the saliency map, or the map of the bits from various locations. Here is a histogram of these bits. The highest bit comes from the location of the input cross, caused by the horizontal bar in a cross. It's an outlier bit with a z-score equal to 7, very salient. And this high z-score agrees with our subjective feeling that the location of this cross attracts our attention. Here are 3 input.
No, it's the other thing. But so we stop just to see whether there are questions so far.
With bid, what do you mean?
Okay, bid is like in an auction. It's like you're auctioning for something. Bid for something, bid value. Yeah. So you say, I'm bidding for attention.
So it's this one.
Oh.
This is the mic.
Oh, that's right. A bid is like you're in an auction. You want to buy something. You say, I bid 10 euros or 100 euros. So you need to bid for it. Yeah. So in this context, that this is a visual input. Each location is trying to get attention, trying to get your, yeah. So they are bidding this value, say, please look at me. And that's the bidding value. And this bid value will be then read out by.
So now I'm looking at you, so you have a higher bid than the screen.
That's right. This is top down. Here it's just the bottom up. Yeah. So the V1, we're talking about bottom up saliency. Remember, saliency is defined by visual input, not by any goals the animal might have. Yes, from the outside input, but inside your brain you have a purpose. You want to hunt for food, and see. You want to listen to lecture, and then so you have this controlling your eye movement from the bottom up ones and top down ones. Top down ones are not talked about here. Yeah, thank you.
Yeah.
Yes.
Okay. At the beginning of the video, you showed an input that had many lines vertically, more or less periodically organized, and at some spots they were missing. My question, and the lines were missing, there were empty spaces. And we saw the response to this signal given by our model. My question is, how does this model take into account the fact of an input that is an empty space? Or
Okay, you may say because this is empty space, yeah.
Yeah.
So it is very bad, yeah. So the idea is, it has 100 million neurons If I simulate them more, I don't have enough computer power. So, so that time was about 20 years ago. I would encourage now people use better computers. Maybe they can do it. This is the reason why, model is never correct. All models are wrong. Some are useful. We're just trying to see whether this is useful enough for us to see that the theory is not crazy. That's why you want to make it as close as possible to real V1, to see that theory is not crazy. Of course, the best thing is to actually test experimentally. Some of these models are testing things that experimentally is not doable yet. But maybe in 20 years, you can do it in real V1. This model is a fake V1. Yeah. So it's like, when Isaac Newton trying to model the sun as a point, the earth as a point, and law of gravity going around. That's also a fake model, but that's accurate, very good. This V1 model is not so accurate, but still one can ask the question, is it good enough to see whether it's not even possible to do this in the model? If it's not even possible to do this in the model, then the theory is perhaps wrong. Yeah, good question. Oh, sorry. What happened? Oh. Why is it not showing anything? Can I just play something?
So this model,
yeah.
okay, it has a visual.
I just stop. But if I stop, why doesn't it show it? It has to play in order to show it.
So this model,
Can I pause
it has a visual input.
Pause. Okay. No.
Hi.
Yeah.
Sorry, perhaps my answer, the previous question had the answer itself. The question was this, that the bow tie pattern that you saw between this disynaptic and monosynaptic, that is like just a model thing. It's not really what is a picture of V1 itself, yeah? So it's not a real picture of V1 itself.
Well, actually, we have some evidence they exist, but we don't know. Gee, why is it not showing when I try to navigate? So maybe I can do not slideshow, but I just do view, normal view. Can you?
So the V1 you are.
I don't want to show this, so this is. How can I make it not show? Yeah, so maybe I just answer the question without your question again. What is your question again?
Are more.
Yeah.
This bow tie pattern that you showed for this V1 model,
Yeah.
that's not, that's like the model property. It's not like really what's a V1.
Actually, there's only partial evidence that this is real V1. We don't know. So the question is like you are trying to build a model with this interaction pattern that has to agree with the real data. And that's why it needs calibration. Otherwise, you can just fake V1 and that doesn't work. Yeah. Mm-hmm. So you say, I need to calibrate and make sure that this works.
It turns out that
You say it has to work. For it to work, can you actually find the interaction pattern to make it work? Maybe you can never find the interaction pattern. If you never find the interaction pattern, this theory cannot be right. Do you see what I mean? Mm-hmm. Theoretically, you can search in a space of all possible connections and it still doesn't work. And it's possible that, some empty space or whatever, then you can play the game. But if you cannot even show a single, let's say you can have one IAJ matrix, I and J matrix to make this work. But to make this work has to be a different I and J. Then you just falsify your theory. Does that make sense? Yeah. Good. So the fact that you can actually find a single I and J matrix to make it work. Now if you work on Ising model, you know the system is very frustrating. So to control a frustrating Ising model is very non-trivial. Imagine you're actually having this kind of a...
Now let's include the neural inputs from neighboring neural pair. So now these terms describe...
This
In addition,
is a very frustrating easing. More than easing, because it's analog. To actually make it work is actually mathematically very complicated. And you cannot even use statistical mechanics because these are asymmetric interactions. There's no Hamiltonian. There's no Hermitian you can do. You cannot do partition function, nothing. So this is a completely dynamic system stuff. And turns out you say, why don't you use Hoffield model? Because the interaction is all symmetric. If you use Hoffield model, you can mathematically prove this will never work. In particular, the spontaneous symmetry breaking will happen. So it turns out the brain does this for a mathematical reason. It has to have the excited neuron, inhibitory neuron, such that, so the brain actually, in the beginning I thought this is hardware constraint. A neuron can only excitatory, only inhibitory. And then you can mathematically prove a Hoffield model will not work. So it's very interesting. Yeah, thank you.
Sorry, so the way in which you prove the model is just obtaining the patterns that you saw in experiments,
Yes.
fitting the functions, and that's...
That's right. Experimentally says there has to be local interactions, not global. So you have to make it local. Experimentally, it is seen that like-to-like interaction pattern tend to project to things that are like each other. Remember, we talked about these projection patterns. They all go to these projection patterns.
This model,
they all go to like. So we also do that. So whatever experimentally is known, we're not allowed to violate. What experiment is not known, we're allowed to adjust in the model. And when you're allowed to adjust, and it's unclear whether you will be able to find a single set of parameters to make this possible. So the fact that you can make a single set of parameters to make this possible is already showing that this might be the case. Yeah.
Thank you.
Okay, I have a simple question. What do you mean by hallucination?
Hallucination.
The model should not have hallucinations.
Yes, very good. Maybe it was a bit unclear here. So the idea is you have to make the model not do this. So if you have...
furthermore, what if we have an input like this?
Okay. When the input is homogeneous, translation invariant, the output is not translation invariant. That's hallucination. Imagine you look at a white wall, and suddenly some part on the white wall make you want to move your eye to it. Then it's like a schizophrenic hallucination. And you can see that this pattern and this pattern, they are two different symmetry. It's like if you stand, you can fall one side or the other. And this is because of mutual suppression interactions by the Hoffield kind of model. They're trapping to energy minimum. These are the energy minimums. If you have Hoffield model, that will happen. But if you have the V1 model,
Was a unit.
yeah.
So
If you have the V1 model where you have excitatory inhibitor cell, then you don't have energy minimum. And then you can, like riding a bicycle, so you have excitatory inhibitor cell. There's no energy minimum. Oh, sorry, I have to play it for you to see.
Here is our V1 model.
Now you have excitatory inhibitor cell, there's no, then this model actually oscillates, and the real brain always oscillates. That's why you have EEG waves. If the brain stops oscillating, the person is dead. So Hoffield model always go to a fixed point, doesn't oscillate. Then it will have the spontaneous symmetry breaking. That's the hallucination. And to avoid hallucination, you can mathematically show that you have to have this brain-like circuit.
Okay, so maybe we go on with the video.
Yes, so this is the kind of a fake test of the model by look at mathematical feasibility. Now that we know this model is calibrated, then we pretend this is actual real V1. And let's see if it works in some non-trivial stuff. So we were here. Yeah.
Here's another example. This is the input to the model and the model response pattern. And here is the saliency map, or the map of the bits from various locations. Here is a histogram of these bits. The highest bit comes from the location of the input cross, caused by the horizontal bar in the cross. It's an outlier bit with a z-score equal to 7, very salient. And this high z-score agrees with our subjective feeling that the location of this cross attracts our attention. Here are 3 input patterns. Each pattern is made of 2 neighboring textures with a vertical border between them. This border appears salient. The texture bars to the left and right are oriented minus and plus 45 degrees from the border, with a 90-degree orientation contrast across the border. This texture border appears slightly more salient. The bars are 45 and 15 degrees relative to the border, with a 30-degree orientation contrast. This texture border is not conspicuous. The bars are 60 and 45 degrees relative to the border, with a 15-degree orientation contrast. Such a small orientation contrast makes the border not salient. Spatial configurations also matter. This border is more salient because some bars are more parallel to the border. Similarly, this border is more salient than the example to its right because some texture bars are parallel to the border. So therefore, comparing these 4 examples, this border is the most salient. This one is the second most salient. This one is still quite salient, but this one is not salient. And this is how the V1 model responds to them. Indeed, the z-scores for the borders are agreeing with our psychological assessments of the relative saliencies of these 4 examples. In each of these 3 visual input images, only one bar is tilted 45 degrees from vertical. All other bars are less tilted from vertical. This unique 45-degree bar appears most salient in this image, so it will be quick to find it in a visual search task. But the same bar is less salient in these 2 images. Here, all background bars are 15 degrees from vertical and spatially regular. It has been known that a feature singleton is more salient when the background is homogeneous. In this image, the background bars are randomly placed, although they are uniformly oriented. Here, the background bars are randomly oriented around 15 degrees, although they are regularly placed. Our V1 model responds like this to these images. The responses to the unique bars are inside a circle. Here, this response is higher than all the background responses, and all the background responses are very similar to each other. This makes the z-score for the unique bar quite high, 3.4. Here, some background responses are higher than the response to the unique bar, and the responses to the background bars are more heterogeneous, so the z-score for the unique bar is quite low. Similarly, here. Homogeneous background gives homogeneous background responses because iso-orientation suppression acting on the background bars is also homogeneous. However, the iso-orientation suppression is not as homogeneous in these 2 cases. Different background bars are surrounded by different contextual inputs. For example, this bar has fewer neighbors, so is under weaker iso-orientation suppression. Here is a simple example of visual search asymmetry. It's easier to find a cross among bars than to find a bar among crosses. Here are the search targets. The V1 model's responses agree with this. At the target cross, the z-score is 7. At the target bar, the z-score is 0.8. The horizontal bar in the cross is uniquely horizontal, so it escapes the iso-orientation suppression from the neighboring vertical bars, evoking a relatively higher response. The target bar is not uniquely vertical in this image, so it is under iso-orientation suppression from the neighboring vertical bars in the neighboring crosses. For the z-score in the cross, the response to its horizontal bar alone determines the z-score, not the combined responses from two neurons, one for each bar in the cross. This is because by the V1 saliency hypothesis, a location's saliency is determined by the highest response to this location. Let's also notice that here there is no need for V1 to have neurons tuned to a cross shape to make this cross's location salient. Our model has just neurons tuned to bars only. So in principle, V1 could be responsible for more complex visual shapes to attract attention exogenously. Here is an example of a feature search versus a conjunction search. In this image, try to find this target shape among these shapes. It's quite easy because the target has a unique horizontal bar in the image. In this image, try to find the same target shape among these two shapes. It's quite difficult because neither of the two bars in the target is unique in the image. The conjunction of these two bars makes the target unique, so it's an example of conjunction search, which is known from visual search literature to be typically difficult. Each bar in the target is under iso-orientation suppression from neighboring bars sharing its orientation. V1 model's responses agree with visual search behavior. The feature search target has a z-score of 3.3, but the conjunction search target has a z-score of minus 0.9. These four examples demonstrate that the saliency of a texture border depends on the density of the texture bars. Each of these four images contain two neighboring textures with a vertical border between them. Each image has a left texture containing vertical bars and a right texture containing horizontal bars. However, the texture border is the most salient in this example, still quite salient here, much less salient here, and least or not salient here. The V1 model's responses agree with these observations. The responses to the background bars are less suppressed when the texture bars are sparser, because each bar has fewer iso-orientation neighbors to give iso-orientation suppression. The z-scores of the texture borders follow accordingly. It equals to 4 here, 3.3 here, but only 2.1 here, and 0.57 here. This image contains a homogeneous texture with just a single bar missing, creating a hole in the middle. This hole appears also somewhat conspicuous. However, one must wonder which V1 neuron is signaling for the saliency of this hole if there's no bar to evoke responses from any V1 neuron to this hole. However, each of these two neighbors has one fewer iso-orientation neighbor to exert diacinetic suppression compared to most other bars. So, relative to most other bars, they should evoke slightly higher responses. Although their responses may be only a small fraction higher, This fraction could be sufficient to give their locations high z-scores for attentional selection if the background responses are sufficiently homogeneous. Attentional attraction by these two neighbors could feel like an attraction to this hole. To visualize small variations in the V1 model's responses, we use gray levels to represent the V1 model's response levels. The response is 0 to the hole. The responses are highest to the neighbors, giving them a z-score equal to 3.9, making the region around the hole quite salient. As a comparison, let's put an orthogonal bar inside the hole. It is much more salient. Of course, the V1 model's response to this orthogonal bar overshadows its responses to all the other bars, and the z-score is 18. In images A and B, the highest responding bars are these ones, and we can see that they have contextual surrounds to give them good collinear facilitation, but weaker iso-orientation suppression. We have seen that this simple example of asymmetry between two visual searches can be easily understood by the absence or presence of iso-orientation suppression on critical bars.
I just like to pause and show that this is like doing an experiment. You look at this fake V1 and see if it works for all these psychophysics behavior. Oh, is it salient? The model says salient. It is not salient. The model says not salient. So this gives you, it's like a test, yeah. But so far the tests are very, you can say, still too trivial. Shall we look at something that's not trivial? Next, let's look at something a bit more complex. Yeah, okay. So, continue. How do I continue?
And here is another example of visual search asymmetry that's much more subtle. On the left is a circle with a gap among closed circles, and on the right is the opposite, a closed circle among open circles. Each circle is sampled as multiple bars in a particular spatial arrangement. Since our V1 model does not have neurons tuned to such a particular shape of open or closed circles, it's only slightly easier to find the odd circle in the left image than in the right image. It's not obvious why this is the case or which single V1 mechanism is responsible for this, whether it is due to a difference in the strength of iso-orientation suppression or in the facilitation between neurons for co-aligned bars, or a combination of multiple V1 mechanisms in a subtle manner. Now, since this subtle example is already observed in behavioral data, it provides a critical test to the V1 saliency hypothesis using our V1 model. So we can ask if the V1 model could demonstrate the same asymmetry. To test this, we submit each of the two images to our V1 model and get the model's responses. And from these responses, we calculate a z-score for each of the bars for the target circle and take the maximum of these z-scores and treat it as the z-score for this circle as a whole, since attention to any bar on this circle is attention to this circle. And we do the same thing to get a z-score for this closed circle in this visual image on the right. And the results are the z-score is 9.7 for the target circle in the left image and is 0.41 for the target circle in the right image. Now, given a subtle behavioral difference between these two search images, the higher z-score of 9.7 suggests that the V1 model is quantitatively quite inaccurate. However, the qualitative order between these two z-scores agrees with the observation that the search is easier for the left image. This agreement is not achieved by tuning the model parameters. We remind ourselves that that the model parameters have been fixed by our model calibration procedure to make the model imitate the real V1. Of course, this agreement could be a coincidence since there is a 50% chance for such a qualitative agreement to occur as to which of these two searches is easier. However, other examples of subtle asymmetries have been observed. In this example, it's easier to search for a pair of convergent lines among pairs of parallel lines than the other way around. Here, it's easier to find a longer line among shorter lines than the reverse. And here, it's easier to find a curved line among straight lines than the reverse. And here, it's easier to find an ellipse among circles than a circle among ellipses. And in all these 5 pairs of searches, the model gives a higher z-score to the easier one in each pair of 2 searches. And so for all these qualitative agreements to happen coincidentally, the chance is much smaller. And these search asymmetries are subtle, and they require multiple V1 mechanisms for contextual inferences to work together to give such outcomes. And except this is an exception, perhaps collinear facilitation alone could explain it. Overall, these agreements between the model and data increase our confidence about the V1 saliency hypothesis.
Okay, so perhaps any other questions? We can also stop. Any questions? Yeah. You just shout louder. Shout louder. Okay.
For the case when we looked at the hole, we focused on the left and the right rods. For the case when we had an empty space between the rods, we focused on the left and the right ones, but similarly the up and the bottom ones have also this lack of neighbor.
Correct.
Yet I think the response was lower for them.
That's right.
Why was that?
Remember, bow tie interaction is not isotropic. Okay. Yeah, that's why. Oh. Good.
Okay. Please, in the case where we had the circle and the ellipse, like you said, it's easier to find the ellipse among the circle. Yes, but I remarked that there wasn't they didn't have the same, almost like the same size. So if they were like the same size, would it still be easy to distinguish?
That's true. But in the experiment, it's also not the same size. So you can say that, could we change it and see what happened and then try in the model? But in the experiment, they did it that way. We have the data on that. So if it's the same size, we should go to a psychology experiment to see which one's easier, then try in the model. That would be good, yeah.
Sorry, so for the example where there are vertical bars and a cross, why is the cross interpreted as a set of 2 bars, one vertical and one horizontal, and they both have different z-scores, and we took the maximum one, if I understand correctly. So why isn't the cross considered as a shape in of itself? Why is it 2 shapes?
Because in V1, there is no neuron tuned to that shape. We are using a real V1 model. We're not trying to model anything outside V1. V1, the only way to look at input is through these bars. You cannot build an arbitrary model, it works, then you call it V1. Then it's not a test of V1 saliency hypothesis. Yeah. It's like if you do experiment, you do test on V2, then it's different. Yeah. That's the idea. Thank you.
Sorry, is it possible that V1 focus on collective patterns instead of just individual? Because there are cases in which the vision tries to see a shape and not just an individual thing that is not consistent with others.
Yes, it's almost the same question. Remember, we need to select a small part of visual input to recognize it. So V1 is trying to make you move your eyes before you recognize it. Remember, we want to have the egg without a chicken. If you already recognize the shape, we don't have this power. Our brain doesn't have the power to recognize, then look. Yeah? We're trying to see if it's feasible to have something as simple as V1 or as stupid as V1. It doesn't have anything to recognize a cross, doesn't have anything to recognize a face, nothing. But still can make you move your eye to it, to its highest firing location. That's it. Okay.
Here we're constantly saying that some searches are easier than others, and we are using that strongly because we're saying that we know that this search is much, much easier than this other one, but our model captures this qualitatively but not quantitatively. My question is, are these senses of difficult and easier based on experiments when people are shown these images and the time is measured?
Yeah.
Okay.
So these ones, I kind of tell you that I just use this data and make you see, is it really easier? Maybe, maybe not. Okay. But, so we use that data. You can see it's easy to find a longer bar than a shorter bar. Yes. Okay. The other ones are very obviously easier. Then I don't even show you the real data. You can use yourself as a real data. It's easier to find this. You are looking, you use yourself as a real data. So most of these days I use the model on the things you can already see with your own eyes. The only place
it's not obvious to test.
Yeah. This
agreement
is
not
so
achieved
obvious.
by tuning the model parameters.
And because it's so not obvious, you think this is time to kill the model. The fact that it doesn't kill gives you confidence. That's another test. Yeah? Because it's so subtle. Okay.
Yeah. If I heard correctly, when you found a z-score of 9.7, you mentioned that it's too high.
Too high.
So quantitatively it's not accurate, but qualitatively it is. Why is that? Why is it?
The model is poor. Just like she said, there's these holes. There's only a single scale. The model is wrong. So therefore, let's wait for a real V1 next. Okay? Because to do such experiment, imagine, can I find a monkey collaborator to do this? Difficult. Yeah. So we use a very poor model. But if the model, here you can say a theorist can play with parameter. So it's a little bit like cheating. If we can't even cheat, then the theory must be wrong. Does that make sense? We're trying to cheat. At least there is a particular parameter region where it enables us to cheat quite well. Yeah. Okay, so now let's use real things that are maybe continue. So maybe just go on.
We remind.
Okay, now we can.
Let's have a visual search task in which human observers search for a bar that's unique. It is an odd one out. In this example, the target bar is unique.
Yeah, just to say now it's real, no more model. Now we really test, first by psychology. And it's a zero parameter quantitative prediction of the theory you really test. And then next we move to a real V1, no longer cheating, okay?
In color, all other bars are identical to each other. Let's say this observer has a reaction time of 500 milliseconds to report this odd bar. For example, the task is to report by a button press whether this bar is in the left or right half of a display filled with such bars. Here is another example. Now the odd bar is unique in orientation. All other bars are roughly the same as in the first example above. Let's say that this time the reaction time is about 600 milliseconds for this example. Now let's have the third example in which the odd bar is unique in both color and orientation, all else being the same. Could we now predict what the reaction time should be? Maybe around 400 milliseconds? Maybe around 500 milliseconds? Vish can predict this third reaction time from the two reaction times above. And this predicted reaction time depends on whether V1 has neurons tuned to both color and orientation. Let's recall that Vish states that the highest V1 response to each visual location represents the saliency or bidding value for exogenous attentional selection at that location. Let's apply Vish to this example. Imagine a simple case when V1 has just neurons tuned to color only and neurons tuned to orientation only and has no other types of neurons. Let these be the firing activity levels of neurons tuned to orientation responding to these bars. And all of them are tuned to roughly the same orientation, namely the orientation of these bars, evoking their responses. They have low response levels since they mutually suppress each other by iso-orientation suppression. Let these be the responses from the color-tuned neurons. All these neurons are tuned to the blue color of the background bar, except this one, tuned to the red color of the unique bar to excite it. And it has a higher response because it is the only one escaping the isocolor suppression of the other color-tuned neurons onto each other. This is the maximum V1 neural response to this odd bar. And according to our hypothesis, this response, relative to the background responses, determines the saliency of this target location. Let's denote this highest response as X. For example, it could be 100 spikes per second. The reaction time to report the target depends on this saliency signal X. According to Vish, the higher this V1 response signal, the shorter should be the reaction time. Of course, the transformation from V1 signals to reaction times involves multiple intermediate steps, such as starting from the V1 signals bidding for attention. These signals are read out, let's say by the superior colliculus, to identify the winning bid. And then the command is sent to the motor regions so that this observer shifts his or her attention to the unique bar and presses a button to report it. All these transformation steps can vary quantitatively from one observer to another. For example, some observers may have stronger muscles to give faster motor responses. But this qualitatively monotonic decreasing nature should hold for all observers, even though the exact shape of this curve can vary from one observer to another. Now we can do the analogous analysis for this example when the target bar is unique in orientation rather than color. Now all the color-tuned neurons responding to these bars will give suppressed responses by isocolor suppression to each other because all bars have the same color and all responding neurons should be preferring this same color. But among the orientation-tuned neurons responding to these bars, the neuron responding to the target escapes the iso-orientation suppression because it prefers the target's orientation that is very different from the background orientations. And this neuron's response determines the target's saliency, and let's say that its response level is Y. For the same observer, we could use the same transformation, and so this response level Y gives a reaction time, and in this example, it should be 600 milliseconds. Let's compare this current case, which gives a 600 millisecond reaction time, for example, with the previous case when the target was unique in color. The reaction time was 500 milliseconds, for example, with a winning bit response level X. Here, the winning bit response level is Y. So therefore, by this monotonic transformation, X must be larger than Y to give a shorter reaction time. We use subscripts to denote the unique feature of the target, C for unique color and O for unique orientation. Now we are ready to examine this case. The target is unique in both color and orientation, and we call it a double feature singleton. These are the responses of the color-tuned cells. The highest response among them is X, from this cell which escapes the isocolor suppression. And these are the responses from the orientation-tuned cells, and the highest response among them is Y, from this cell which escapes the iso-orientation suppression. So therefore, the winning bit is the larger one between these two responses, X and Y. Whichever cell responding to the target is more activated, its response dictates the saliency of the target. And then by this monotonic transformation, the reaction time to this double feature singleton target should be equal to the minimum of the reaction times for the corresponding single feature singletons. Therefore, applying our prediction here, given these reaction times, Vish predicts a reaction time of 500 milliseconds. We remind ourselves that this prediction comes from assuming a simplistic V1 without any neurons tuned to both color and
So here we have an example that you can, Here we have an example you can predict something precisely. No single parameter, 500 milliseconds. Imagine you go measure experimentally. You find at 400 milliseconds, the theory is falsified. 495 is it falsified? It depends on your clock, whether it's 5 milliseconds is your error. So the theory is not very easy to falsify. 600 milliseconds, the theory is also falsified. Okay? So let's see.
So I have a question. So can you think that this hypothesis that you choose the maximal, say, firing rate or the maximal signal, it's actually a consequence of the fact that you get the minimal reaction time, in the sense that is the signal that comes first that prompts the response.
So you can say economically, it's a very cheap design for the brain. You want to be quick. You don't want to recognize the tiger first because it takes you computation. You just say something's there dangerous, let's run away. Yeah. And so this also, of course, theoretically enables us to predict so quantitatively. So now we are in a good chance to falsify the theory, so let's try it.
Orientation. Usually, reaction times are not fixed to a single value. Across different trials, the winning V1 response for the target fluctuates. In one trial, it may be 100 spikes per second. In another trial, it is higher or lower. And this should cause fluctuations in the reaction times, which has a distribution over trials. Similarly, we can have another distribution of reaction times for the orientation singletons. Then, this Vish prediction enables us to predict a distribution of reaction times for the double feature singletons using a Monte Carlo simulation. This is done by randomly sampling a reaction time from this distribution for the color singletons and take another random sample here for the orientation singletons, plug these two samples into this formula, and this gives you one sample in this distribution. And repeat this process, you can get a whole distribution of reaction times for the double feature singletons predicted from reaction time data from the single feature singletons. Here is an example set of experimental data on these distributions from an observer for the two single feature singletons. We can then predict the distribution for the double feature singleton and compare this prediction with the actual distribution for this double feature singleton measured in the same experiment. Here we show the predicted and observed distributions on the same plot to make a better comparison. The blue and red curves are for the predicted and observed quantities respectively. On average, the observed reaction times are shorter than the predicted ones. And this is also the case in data from a few more observers. It turns out that this is because our prediction assumes a V1 that is too simplistic, such that the assumed V1 does not have any neurons tuned to both color and orientation. So let's come back to our drawing board for the double feature singletons. We consider that real V1 has neurons tuned to both color and orientation. We have responses from neurons tuned to color only, and the largest response among them is X to the target, and responses from neurons tuned to orientation only. The largest response among them is Y to the target. Now we add a third group of neurons tuned to color orientation conjunctions, and let this neuron type's response to the target be denoted as Z. Then the maximum response to the target is the maximum of X, Y, and Z. And this could be larger than the original maximum just over X and Y only. Then, according to our theory, this perhaps a higher bit should lead to perhaps a shorter reaction time. Therefore, the original prediction should be revised by this one. Essentially, this equal sign is replaced by a less than and equal sign. And this quantity is called the race model prediction. Therefore, in real V1, the reaction times for the color orientation double feature singleton may be shorter than predicted by a race model from reaction times for the corresponding single feature singletons. This explains such data in some of the observers because this blue curve is from the race model prediction. In summary, with RTC for the color singleton and RTO for the orientation singleton, then for the color and orientation double feature singleton, the reaction times are likely shorter than predicted by the race model. This inequality, rather than an equality, is because V1 has neurons tuned to color and orientation simultaneously. Now we can apply the same argument to the case when the color feature is replaced by a motion direction feature. In this case, all bars have the same orientation, just like the case to the left. An arrow on each bar visualizes the direction of motion of the bar, so therefore this bar is the singleton. It is unique in its motion direction only, moving to the left, while all the other bars are moving to the right. Now let RTM be the reaction time to find this singleton. So here the subscript M denotes that the unique feature is in motion direction. Here is when the singleton is unique in orientation only, and all bars move in the same direction. And the reaction time to this singleton is RTO. Now, this is when the singleton is unique in both motion direction and orientation. The reaction time for this double feature singleton is also likely shorter than that predicted by the corresponding race model. And now, because V1 also has neurons tuned to both motion direction and orientation, note that these two inequalities are the same, except that the subscript C for the color feature is replaced by the subscript M for the motion direction feature. So here we have a triplet of singleton cases involving features color and orientation, a second triplet involving features motion and orientation, and now we can extend to a third triplet involving features color and motion direction. So this is for a singleton unique in color only, all bars move in the same direction. And this is for a singleton unique in motion direction only, all bars have the same color. And this is for the corresponding double feature singleton unique in both color and motion direction. However, the reaction times for this double feature singleton are predicted to be the same as that by the corresponding race model, because V1 has few neurons tuned to both color and motion direction. So if we plot reaction times versus the three types of double features for the double feature singletons, and if the race model predicts these kind of RT values, then Vish predicted RTs should be shorter than the race model predicted one when the double feature is CO, color and orientation, and also when the double feature is MO, motion and orientation. But the Vish predicted RT should be equal to the race model prediction when the double feature is CM, color and motion. This is a signature of V1 since it uses the V1 property that V1 has neurons to feature conjunctions CO and MO, but not CM. However, a signature of higher cortical areas, such as V2, will be like this. All the reaction times should be shorter than the race model predicted ones, because the higher cortical areas have neurons tuned to each of these three kinds of feature conjunctions. The experimental data supports the prediction by the V1 signature, and this suggests that higher cortical areas are not involved in visual saliency, at least for these kind of visual input stimuli. We have seen that in a simplistic V1 without any neurons tuned to both color and orientation, V1 saliency hypothesis can quantitatively predict the reaction time for a double feature singleton that is unique in both color and orientation, given the reaction times for the corresponding single feature singletons. No free parameters are needed to reach this quantitative prediction. A whole distribution of reaction times can be predicted accordingly. However, we have also seen that if V1 does have neurons tuned to both color and orientation, then this race model equality no longer holds, but should be replaced by this inequality, so that the reaction times are likely shorter than predicted by the race model. This inequality means that this reaction time can no longer be predicted precisely in its quantitative value. We have pointed out that the race model can hold when the two feature dimensions involved are color and motion direction. This is because experiments have found few V1 neurons tuned to both color and motion direction. One may question whether this can be certain that neurons tuned to both color and motion direction are absent in V1. Whether a neuron is found to be tuned to some features or not may depend on the observation criteria and is also likely to depend on the statistical properties of the visual input environment. However, by adding one more requirement that these neurons would have to be tuned simultaneously to all these three feature dimensions, color, motion direction, and orientation, then one could be more certain that few such neurons are present in V1. Then one can extend this race model involving two feature dimensions to this one involving all the three feature dimensions. Each of these three reaction times are for single feature singletons, unique in color only, motion direction only, or in orientation only. Each of these three reaction times are for double feature singletons, unique in both color and motion direction, or in both color and orientation, or in both motion direction and orientation. And this is the reaction time for the triple feature singleton, unique in all the three feature dimensions. This is a schematic of a single feature color singleton visual input. Each bar is not only colored and oriented, but is also moving. An arrow indicates the direction of motion, so here all the bars are moving to the right. All the bars are oriented clockwise from vertical, but the bar that is the odd one out is unique in color only. This is when the odd bar is unique in motion direction only, and this is when the odd bar is unique in orientation only. These are for the three types of single feature singletons, and these are for the three types of double feature singletons. This singleton is unique in both color and motion direction. This one is unique in both color and orientation, and this one is unique in both motion direction and orientation. And the triple feature singleton is unique in color, motion direction, and orientation. Once the reaction time for the single feature and double feature singletons are measured, we can predict the reaction time for the triple feature singleton by this race model equation. So for example, if these are the respective reaction times for these three single feature singletons, the minimum among these reaction times is 0.58 seconds. And if these are the reaction times, respectively, for the three double feature singletons, and the minimum among these is the 0.45 seconds, then we can apply this race model equation and we get this equation. With this minimum for the 0.58 second here, and with this minimum for the 0.45 second here. And so we arrive at a quantitative prediction of this reaction time as 0.45 seconds without any free parameters. Since reaction times are statistical, we measure the respective distributions of the reaction times for the single feature singletons and for the double feature singletons to predict the distribution for the triple feature singleton without using any parameters. This is an example prediction compared with the experimental data, which is the actual observed distribution of the reaction times. The prediction matches the data well statistically, and this example is from data by a particular human observer. This test of the V1 saliency hypothesis can be repeated in other observers, and these observers differ from each other in their distributions of the reaction times, but in each of them, the prediction matches the corresponding distribution. Let's remind ourselves that for the color orientation double feature singletons, the reaction times are shorter than predicted by the race model. And this is because V1 has neurons tuned to both color and orientation. In contrast, because V1 has few neurons tuned to all these three feature dimensions simultaneously, the prediction here matches the data. However, higher visual cortical areas downstream from V1 along the visual pathway do have many neurons tuned to triple conjunctions of features. So if they contribute to the visual saliencies of the singletons here, we may observe these reaction times shorter than predicted. Now, since the data confirm the prediction, this is not only a support to the V1 saliency hypothesis, but also suggests that V2 and other higher visual cortical areas do not contribute to the saliencies of these highly salient singletons that pop out to attract our attention so strongly to give such short reaction times.
So perhaps people can ask questions here. So this example, again, sorry. So this example, I feel like maybe particularly interesting to physicists because the idea to have a clean theory, no models involved, no approximation, you just have an equation without parameters. You have to go measure experimentally. And so it's very encouraging that we can have such things happen in biology. And this is one of the first examples. Maybe it will happen more in the future. We have more and more examples happen. Okay, and then any questions?
Quantitative predictions without free parameters.
Any questions? If not, we just go to a real monkey. Okay, you can do experiment, psychology experiment. You can also go to biology experiments. So let's just
relatively easier to falsify if the theory is incorrect. This confirmation of such a prediction provides a strong support to VISH. Various predictions from VISH have been tested and confirmed by behavioral and imaging experiments. Now let's show some evidence from V1 neural responses in behaving monkeys. In this study, the monkey is first shown this image in each trial and should fixate the gaze at this location at first. After the fixation is verified, these bars appear. All bars are uniformly oriented except for an orientation singleton. The monkey should quickly find where the singleton is and make a saccade to it as quickly as possible. In each trial, this singleton could appear randomly at one of the 6 possible locations. For example, it could be here in a different quadrant, or a different location in this quadrant of the visual field. To get rewarded by a zip of water for a trial, the monkey must make a direct saccade to the target from the central fixation point. Indirect saccades are not rewarded, and of course, incorrect saccades like this one or this one are also not rewarded, and the monkey is also not rewarded if the saccade takes too long to start. In some trials, the singleton target is in the restive field of the neurons whose activities are being recorded. And since it typically takes at least 200 milliseconds for the monkeys to start the saccade, the neural responses before the saccade can be observed. So we can ask, if a trial evokes a higher V1 response to the target, is it more likely for the monkey to start the saccade more quickly and to aim the saccade more accurately? This is indeed observed. These are the V1 neural responses during the initial 200 milliseconds after the bars appeared. The neural spiking rates are plotted against the time starting from the onset of the bars. The firing rate peaks quickly at around 50 milliseconds and then decays before the saccade starts. The red curve is the average across trials in which the saccades were faster and also aimed correctly. And the blue curve is the average across trials in which the saccades were slower or aimed incorrectly. And this significant difference occurs at a latency of 40 to 50 milliseconds from the appearance of the bars. And this short latency means that these V1 signals cannot come from some feedback from higher brain areas or from the superior colliculus. This response difference is for when the Sakar target is tilted 90 degrees from the background bars, so the target is the most salient. And these are responses from neurons whose preferred orientations are more similar to the target's orientation. And we also emphasize that these two response levels in V1 neurons and in monkey behavior are for the same visual input and with the same 90-degree orientation contrast between the target and background bars. When the orientation singleton target is less salient, by having a smaller orientation contrast from the background bars, the initial response difference is smaller when the monkeys were less trained in this task. And of course, their task performance for less salient target was also worse. These V1 neural activities, linked with ongoing saliency behavior of the monkeys, provide a strong support to the V1 saliency hypothesis.
Okay. Very good. So I think we are done for today, unless there are questions. Otherwise, I guess you are all waiting for the lunch. So, okay. So thank you very much. The attendance sheet, please. Can you return it back? Yes, thank you. Okay. Yeah, it's okay.